Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage. Are you ready?
Debate fans,
Are you ready?
for the handful in attendance and the thousands watching across the world, brought to you tonight by Jeranism, the #1 YouTube channel in all of existence. Ladies and gentlemen,
Let's get ready to rumble!
Make sure your argument is tight. Wait, what? You must got proof if you so right. Wait, what? Don't get dismissed on false claims, cause you gotta bring the truths and the facts. It don't matter if you're talking about racism, sexism, scientism, paganism, socialism, communism. Talk about capitalism, atheism, globalism. What about creationism? It don't matter what the ism. Live on Debatism.
All right, are you ready? We've got another Debatism for you this evening. It is on to episode number 23 of the regular type. We're not doing Debatism X tonight. We are doing Debatism with self-submitted formats, which is weird, but nonetheless, it is going to happen. It is episode number 23 on the 23rd, and that means something. I don't know. We'll have to ask somebody who's into numerology. What does that mean? It is April 23rd. If you're watching this any other day, it's not live. If you're watching it on the 23rd, it's live. We've got MCToon going against Allan from Space Audits. Let's bring them on, and we were almost ready to do that, but not quite yet. Give me 1 second. We will get this done. So if you want to support the guys or support me and ask them questions at the same time, we can do that. You just go to Super Chat on YouTube, or you can go to Rockfin and send a tip, and I will ask the guys at the end of the debate whatever question you want me to. So that's coming up at the end, and I guess we can have Allan here. There we go. We'll have Toon come on first. Toon, go ahead. You can say hello to everybody while I fix Allan's screen. Just take a second, but go ahead. Welcome.
Hello, everybody. I was just informed that I ladle manure.
All right.
It's been a while since I've had to do that, but welcome everybody. Thank you for joining us. Thank you for having me on, Jaren. It's always good to be here.
Indeed. And we've also got Allan, your opponent this evening. Allan, welcome to the show.
Hey, thanks for having me on, Jaren. Much appreciated. Toon, thanks for being here. Looking forward to getting into our general relativity.
Yeah.
All right. Are we doing just general, or is it special? Tell us what the topic is, since I know
So
not.
the topic will be general relativity, on the correctness of general relativity, and it's put up by, it's kind of stitched together by three main proofs: the perihelion precession, the gravitational lensing effect, and what's the other one? Gravitational redshift. So the first one's kind of like a post-diction, so it's not really a good proof. So we're focusing primarily on the starlight displacement, so gravitational lensing, and gravitational redshift, meaning the frequency shift in light due to gravitational effects.
Okay, that works for me. And we're going to do a coin toss, and then you guys are starting with, 12 minutes? The intro,
Yep,
I believe.
yeah.
Okay. Let's do the coin toss. Let me get that on the screen for you. Hopefully you can see it. Well, it's kind of shouldn't be see-through, but for some reason it is. See it up there? It's got the right now. It's got the Modern Day Debate logo on there. You can choose Debatism X or Modern Day Debate. Who wants to choose? Let's have Toon choose.
Which one is Tails?
Tails would be
Modern Day
Debatism
Debate.
X.
Oh, all right. I'll take Tails then.
Okay, here we go. He chooses Debatism X, which is clearly the better show, and he wins. All right. Going first, going second. What do you want to do? Choices.
I'll go second.
Okay.
Nice.
And that means you're going to start out, Allan, and you're going to have 12 minutes, right?
Mm-hmm.
Okay.
Whenever you're ready, good sir.
Yep. And then do you want me to tell you when you have a minute left or so? I will tell you when you have a minute left.
Just say 1 minute or
Okay.
whatever in my ear.
Sounds good. And we're going to turn that off. Great. All right, whenever you get started, I will start the clock.
All right, cool. So we'll go ahead and get into it now. So this is on the alleged experimental and observational proof of general relativity. So in 1905, Einstein released his first mixtape titled On the Electrodynamics of Moving Bodies, where he disses the ether in his first track, and then it goes on to explain that the motion, or goes on to explain relative motion through a constant velocity, and he says that the speed of light is always the same for inertial observers. In 1915, he releases his first LP called The Field Equations of Gravitation, where he's extending his theory to a theory of gravitation and acceleration, linking the two with the equivalence principle. For acceptance of the theory, it must be able to explain the frequency shift in light and the displacement due to gravitational influences. So the principle of the equivalence principle states that an accelerated frame is equivalent to an inertial observer in a gravitational field. So in other words, this means that an observer in a gravitational field would experience the same amount of length contraction and time dilation relative to the magnitude of the gravitational field or acceleration. So Einstein shows here that by taking partial derivatives from the space-time metric g mu nu, that it reduces back to Newtonian approximations for objects moving at low velocities or when they have low mass. So this is extremely important because it extends Newtonian dynamics to the solar system, which gives physical meaning to the geometric expression of space-time, which is said to be where Newtonian dynamics emerge from, right? So we're going to learn more about this theory so we can learn and understand the tests that are put forward to prove the theory. So here's the modern formalization of the field equations. Going from right to left, we have the stress mass energy tensor, and there we have the distribution of the gravitational field through space-time. And then on the left-hand side there, we have basically that just describes space-time curvature to be brief. And then the idea here is that we're going to conserve mass, energy, and momentum into a field that's distributed over space-time, which causes curvature. A manifold is a curved surface that can be treated as locally flat by adding a time axis perpendicular to the spatial axis, or to the spatial x-axis. In an XYZ coordinate system, space-time is created. And again, just conserving mass and energy into the gravitational field causes the curvature. So the gravitational field causes hyperbolic curvature of the localized manifold, leading to space-time curvature. So this requires a new definition of orbital mechanics for objects in motion through the gravitational field. There'll be their orbital path is described by what's called a geodesic. A geodesic is defined by the shortest path between two points in space-time, accounting for a curvature. So in the third dimension, the geodesic will appear to be linear and straight, and in the fourth dimension, you would see that you're actually traveling around curvature. Gravitational fields bend space-time, causing celestial bodies to move along these curved paths in free fall. Gravitational effects, i.e. the illusion of mass attracting mass, is an emergent property of this space-time curvature within the localized manifold. Now, that all sounds very fantastical, but let's get an easier way to look at it, right? So we have a graph here with two observers. We have an inertial observer represented by t and x, right? And then we have t prime and x prime, and then we have an angle, or we have theta here in between them, right? So this represents the amount of divergence in time and distance between an observer who's in a gravitational field or experiencing acceleration relative to a stationary observer. So that's all that math describes. It's just a hyperbolic curvature between two different reference frames, right? So that's all cool abstract mathematics. How do we make it meaningful? How do we get it to apply, right? So we're going to go through some astronomical and lab experiments and observations that are put forward as the proof. So the perihelion precession, which is a post-diction, so not a good proof. And we have the deflection of light rays, which is a prediction based on the magnitude of the displacement, or which is based on the magnitude of displacement, which will help distinguish relativity from the classical theory. And then we have gravitational redshift, which will mechanistically describe how light interacts with the gravitational field in the form of frequency shift, i.e. retardation in the frequency. So we'll be focusing on 2 and 3 primarily because the first one's not a good proof. Second, so to analyze the first proof, we have to know what an arc second is. So if you look at the distance between 1 and 2 degrees, you break that up into 60 sections. You have 60 seconds of arc, and if you break each minute of arc into 60 seconds, you have 60. You're just multiplying that. So you can break 1 degree of arc. You can break 1 degree into 1/3600th of a degree. So that's how the sky measurements work. So general relativity predicts that starlight will be displaced due to the presence of a gravitational body, because traveling along a geodesic, which is a curved path, the gravitational field will curve space-time. It is stated that Einstein predicted that starlight will be displaced by 1.75 arc seconds, whereas the Newtonian prediction was that the starlight would be displaced in the gravitational field of the sun by 0.87 arc seconds. 1 second, gotta get some water here.
No problem.
So additionally, without getting into the quantization of light, these two theories have different conceptualizations about how light behaves in a gravitational field. So for simplicity's sake, let's just say that the mass attracting mass theory makes a different prediction than the space-time theory. So here we have Einstein's derivation for the displacement. Here he says that the alpha is equal to 4km over c squared r, which is in big K, or I'm sorry, K is big G, m is the mass of the sun, c is the speed of light, and r is the radius of the sun. So it's just a ratio against the speed of light to give them their angle there. And so to test these observational wise, there was an eclipse coming up in 1919, May 29. So Arthur Eddington and his boy Cromlin set out to Sobral, Brazil, and the island of Principe off the west coast of Africa to take observations. All of Cromlin's data was unusable due to thermal expansion and contraction during the eclipse, so they threw all his data out. 2 of Eddington's plates survived with 4-star distribution, where only displacement was observed at the solar limb, so 1 solar radii. So he takes the photographic plates back to jolly old England, and they get together, the boys at the RAS and the RS can get together November 6th and have a meeting, and they say, okay, Eddington proved that this is a successful confirmation of Einstein's theory. But however, at the meeting, there was some objections raised, which we're going to get into and follow up on. So the transcripts from the meeting, a man named Dr. Silverstein chimes in, and he says, he's basically saying if there's starlight displacement in accordance with the relativistic prediction, there must also be a redshift observed in accordance with the magnitude of the gravitational field to establish a cause and effect relationship, because at the limb of the sun, there's already assumed to be a plasma, an electric field, a magnetic field, gas, different temperatures, pressures, etc. So the theory would have to compete with, going through a different medium, like a refractive index change, essentially. So at that location, the results are, ambiguous at best, and it can't be stated that this is proof of the theory. And at the time, there were 2 gentlemen, spectroheliograph operators, who were world-renowned at that time, Charles St. John and John Evershade, who were tasked with making the redshift observations, and they actually took observations during the eclipse and found no redshift that corresponds with the interaction of a gravitational field for the starlight. So let's see, we'll come back to this guy. So a guy named Edward Dowdy Jr. does his own derivation for starlight displacement, and we're going to see a familiar equation here, but basically, well, the only thing he changes is the story of the radius of the sun. So instead of it being a giant gas giant, he describes it as a plasma. He uses, instead of the radius for a giant, gas plasma, he describes it as a Gaussian surface, so that he can simplify the electric field of it, so that he can calculate the plasma, right? So it's literally the same equation. So this is, again, competing with general relativity, because the starlight displacement only occurs in the solar limb. The theory predicts out to 8 solar radii. No one's ever seen starlight displacement past the solar limb. So here's a recap of Dowdy's derivation here. It's identical to Einstein's, pretty much, just change the letter there. Okay, so now we're going to get into redshift. So typically for astronomical observations, you look at starlight through a telescope. It gets split through a diffraction grating into a rainbow, which gets projected onto a plate. You analyze the plate, look at the colors, and from there you're looking for frequency shift, because that's going to change the color. So you're looking for more red or more blue or what have you, right? So if you get colors corresponding to that, then it means your theory, people are more likely to believe the story that you're telling, right? So the history of gravitational redshift observations for general relativity is kind of a disaster for the astronomical side. It took like 20 or 30 years before anybody could even come to an agreement of a proper derivation and everything for redshift. So we're going to skip straight to the laboratory here. In 1960 to 1965, Pound, Rebka, Snyder, using a specific energy frequency, emitted energy at the top of a tower, where the energy is going to go to the bottom of the tower, and there's going to be, they expected a gravitational redshift due to the potential at 75 feet versus at at 0. So they used a Moss power detector, which just detects frequency, converts it into an electric signal. The detector was only set to accept a frequency of the expected shift when it starts at 75 feet, and then the potential reaching 0 at the bottom. So that frequency shift that would happen, it was only set to detect a frequency of that amount. They did get a successful detection. Well, in their paper, though, they state, and in the first paper, because they did 2 experiments, but they explicitly state that they can't make any, based on the detection method, they can't make any determinations between relativistic physics or classical physics, because they both actually make the same prediction for frequency shift in that regard. Only the classical prediction is c plus or minus v is not equal to c, meaning that there's a velocity change and not just a frequency change, because in relativity, in the conceptualization of how light works, when the frequency changes, the wavelength inversely proportionally changes to compensate to maintain the same speed. So this experiment can't tell if the speed of light stayed the same, but the frequency was there. So they suggested that they should redo the experiment with atomic clocks at the top and bottom, so that they could time it out and see if relativity holds true or if classical mechanics holds true. This experiment was never conducted, and these men were given the Nobel Prize shortly after. So the problem here, which I just elucidated on, was that it can't distinguish between c plus or minus v equaling c or not. So how do we remedy this? Well, we do vertical interferometry. Here's 2 gentlemen from YouTube that did vertical interferometry setups. They both measured 2 fringes, and then a third guy confirmed it, named Chris Machado. Okay, thank you. Who confirmed the effect for the vertical interferometer, reaching 2 fringes. Right, so there is a displacement. Now, what this means is that the speed of light going up and down is not the same, and that's not a prediction of relativity. That's a falsification of the mechanism of how they say, 1, how light works, and 2, the interaction with the gravitational field. It's not up to snuff, as they say. So here we have a video also of Ken Wheeler showing frequency shift with relative motion through a field. This is known as the Stark and Zeeman effect. When electromagnetic radiation goes through a magnetic or electric field, there's retardation in the frequency, which can change the wavelength. So you can actually watch Ken with a ferrocell and a magnet move the ferrocell over the magnet, and he changes the polarity of light there, and it'll shift from red to blue on the opposite sides when he's moving it over. So these effects are well known. There's other mechanisms to explain these frequency shifts. They're not mutually exclusive to relativity theory. And that's pretty much it. So we can wrap it up there.
All right, great. Time's up anyway. Toon, so now he asked you a 30-second question, correct? If I remember.
Alan asked me a question, I think.
Yes.
Oh, okay. I asked you a question. Okay, cool. So let's go. Let me pull up my questions here. Okay, we'll start with question 1. How can it be said that the general theory gives mutually exclusive predictions for an amount of starlight displacement at the solar limb, when using classical mechanics and the least action principle, as Edward Dowdy showed, you can make the same starlight displacement assuming a plasma medium at the solar limb of the sun?
A plasma medium at the solar limb of the sun would need to be substantiated, but also the shifting has been measured farther out than just at the solar limb of the sun.
How far out has it been measured out? Like, because it's like literally nothing. They even do radio interferometry with it, and it's like it's at the solar limb. There's nothing out past that.
I think you haven't read up enough. I'll cover it. That's in my presentation.
Okay.
So. Yeah.
Okay, you're supposed to.
All right. Well,
minute and a half. You're supposed to have for a response. You need that.
Well,
if he's got contrary evidence, he can do it in this presentation.
Yeah, it's been measured. It's been measured farther out than that. But I would need to see the substantiation that that amount of plasma reaches that far out. What's the actual radius that he's talking about there, Alan?
At the solar limb, bro. It's like literally not anything past 1 solar radii, essentially.
Yeah, I've seen his papers, and he's saying that the sun is 150 million kilometers away, and that it's whatever size it is at the
Yeah.
the limb.
Yeah. So
I mean, if your claim is that the sun is 150 million kilometers away and that it is the size, whatever diameter of the sun we say it is, then that okay, that's an interesting position, but I still need to see the substantiation that that there's that much matter at that
gotcha.
positions.
Well, luckily for me, regarding the derivation, it's just a ratio that changes proportional to the radius. So the distance and size and all that, and the masses, those are just constants that are applied to it. So the angle derived would be the same. So it doesn't, like, the distance is irrelevant. Like, he even so he changed the entire makeup of the sun, and it's just about the radius. So it doesn't matter. It's not the way that you try to attribute that as proof of, like, the distance of the sun to reify it. It doesn't apply.
Okay, we got now your 12-minute response.
Okay, so this was a little bit different than we did last time. So my response was going to be in Redshift. So I'm going to focus mostly on Redshift. So give me a second here to pull it up.
Okay.
All right. So, and then bear with me for a second here. So, okay, and I'm going to share my screen here.
Okay.
Sharon.
Yep. I see just you there for now. Okay.
There you go. Okay.
And I'll add us back on there. Just one second. Go ahead. Whenever you start, I'll start the clock.
All right. So here is I've got a list of different gravitational redshift experiments. Specifically, they're not generally like the Pound-Repka style. So part of the gravitational redshift is that clocks will have a different rate when in a different gravitational field, and the relationship is actually pretty simple. It's I'll show you in a second here. So here is a lab-based test of gravitational redshift with the miniature clock network by Zhang and et al., including Shimon Kolowitz. So he has some Shimon does some good speeches if you're interested in looking at them. Anyway, so they measured a gravitational redshift in the difference of 1 centimeter vertically. And this is the formula here. You got delta F over F. So that's a change in frequency with respect to frequency equals G. That's the downward acceleration times delta H. That's the change in height over C squared. So that's the formula, the prediction according to general relativity. And so this is what they're testing in this particular experiment. So here is a diagram of what they did. So this vertically here, this on the left, you can see this is a total of 1 centimeter tall. And then they have these different, this is an optical lattice where they've trapped strontium atoms and they've cooled them down so that each of the electrons are at their base state. And then they excite them. And so what it's doing is measuring the excitation between the base state of the electron and the one state up. So that's the shell of the electron, and it emits a photon then when it drops back down. So that establishes the clock. And they have multiple ones because they're always getting the atoms in and out of that state. So they do have a really nice error budget. So they go over the details of the error budget here so that they don't have anything that's going outside of their results. So they're sitting down near 0 Kelvin, and they're measuring the difference in the clocks at these different elevations in gravity here and comparing to the prediction. So the data analysis, I'll just jump down to the conclusion here is right here. So they measured the local gravitational acceleration 9.803 meters per second squared. And the final frequency gradient here is they're fully consistent with the expectation redshift gradient within 1 sigma total uncertainty. So this was much later than Pound Repka in 1960. So that's one. Oh, the nice part about this is a nice one. It was blinded. So what they did is oh no, where do they say that? Yeah, it's a blinded test. So what they did is the experimenters, people outside other than the experimenters, added some randomized data to the results, so that as the experimenters were manipulating the data, they had no idea whether or not it matched or didn't match the expectation of general relativity. And then only when they were all done with all of their computation and all of their work was the data unmasked. So that the randomized data then was subtracted back out of it so that they could get the final results. And Shimon talks about that in one of his speeches there, and how it was it kept them honest, because they couldn't fudge anything. They didn't know until after everything was done what was going on and what to expect. So that's the most recent one, just in August 2023. But there's no shortage of them. Here's another one: resolving the gravitational redshift across millimeter scale atomic sample. Atomic clock performance, enabling geodesy below the centimeters level. So all these are much better than what Pound Repka was doing, where they were sitting, multiple stories of a building apart. One more on this: the apparatus is inside of a metal chamber. It is a Faraday cage, so it's one of the things that are well controlled in there. They also controlled for temperature. They discovered in their work that the viewing window modified the temperature, so they had to put in additional controls to keep the temperature consistent at so that the proximity to the viewing window was neutralized. So, all right. How much time do I have left?
6 minutes, 45 seconds. You should be able to see it on the
6
screen.
minutes.
Do you see it on the screen? Or no?
Oh, no, I don't. You're not sharing to me. I to Zoom.
Oh, not?
There, I can see it now. All right. Well,
there you go.
There it is. Okay, thanks. So let me pull up. You were asking about VLBI, and I don't want to spoil everything for my second presentation here. So I will instead, I'll jump to, there we go. I'll jump to this one here. So this is an optical measurement of the deflection by Donald Bruns in 2017, at the eclipse in 2017. He did this in Wyoming, and now we've got a picture of him right here sitting at his table. And so he did a ton of controls, more controls than any of the other types of experiments of this nature. They stopped doing them in 1973 because radio measurements were significantly more precise. So he was within his final measurement is 1.752 arc seconds. And I'll get into a little more detail on what that means in the next presentation. And his the prediction is 1.751 arc seconds. So his uncertainty was only 3%. So he has greatly improved on other optical measurements. And I messaged him. He had a group of about 12 different researchers in different groups that were working on this at different spots for the last eclipse here, week and a half ago, or it's about 2 weeks ago. And let me show you his, so this is some of the actual data. This is just in a PDF, so it's not high resolution, but this is the data that he got of the photographs. He part of the procedure was that after the photos were taken with the telescope, he put a cover over the end of the telescope and took several photos. You see here where we get the telescope again. Took several photos to determine the pixel by pixel light sensitivity, and then took several photos with a LED cover over it, so it was completely saturated again to get the total dynamic range of the pixels, to get a baseline for them. He also, before the eclipse, he moved the telescope 7.4 degrees to the left and 7.4 degrees to the right. Then after the eclipse, there it is. To control for the shape of the wavefront due to the lens coming through the telescope, compared to the shape of the imaging CCD, which is flat. The light coming from the lens is a paraboloid shape, and the lens is flat. So normally we don't see things like that with our own eyes, but when you're doing this type of fine measurement, you want to control for that. So it's one of the things he controlled for, and that gave him a linear and quadratic parameterization of the actual positions of the pixels as they relate to the sky. So, and to make it real clear, he used the Hipparcos data, which is accurate to 0.002 arc seconds or milli arc second precision for where stars are actually located. So he's able to get much better precision in that than like Eddington and the other eclipse expeditions were up until 1973, because they had to get plates either at 6 months later or 3 months later of the same stars, or there were different methods that they'd use to do something similar so that they could measure the positions of the stars, where we now have Hipparcos data that's millimeter arc second accurate. So, all right.
Minute 15.
How are we doing?
Minute 15.
Minute 15. All right. Well, what I'm going to do, I'm going to ask Allan. Okay, can I jump ahead to that, please?
You can.
All right. Allan, what is Einstein's cross? How do you explain Einstein's cross?
Talking about an Einstein ring?
Einstein's cross is a specific instance of it. There's four different.
Has anyone ever seen one with their own observations? Or is it just data that you get from, the Deep Space Network? Because if no one's put their eyes to a telescope and seen an Einstein cross, I don't know. Because apparently you can do, Dowdy showed calculations where, due to gravitational influences and whatnot, the whole sky should look like, Einstein rings and mini Einstein rings and whatnot. So when you say that, what are we talking here? Are we talking DSN or are we talking opticals with the eyes? Can you hear me?
I wasn't interrupting you. I just.
Oh, sorry. Yeah, I'm putting it back to you. What are we talking?
All right. So you don't have a response. Okay.
Can you hear me?
I can.
We heard you.
Yeah. So have you seen an Einstein ring with your eyes, or is it just from images from the Deep Space Network, from satellites looking out into space?
I don't know. That's not an answer to the question, though.
You said, how do you explain it? And is it even real? Do I need to explain something that no one's seen? Is my question.
If that's your standard of evidence, then you're going to have a hard time with any evidence that you bring.
Okay,
right?
Dude. Are you able to substantiate the Einstein ring or no? Is it just something you believe exists and you want me to explain it? Because the deflection derivation comes from the same one that predicts the Einstein ring that no one's ever seen. So that's my answer. And if you don't have an answer for that, then, I guess touche.
All right.
Okay. That's his minute and a half response as well. So then we're supposed to have a 12-minute exchange.
All right, 12-minute exchange. Oh, sorry.
Yeah. Okay.
Unless you have more comments on
Cool.
that. Got a minute or so.
Did you have any other comments, questions?
Do you want to tell us what an Einstein ring is?
Yeah, and there's one in particular that is that you see 4 different copies of the same object behind something that's been gravitationally lensed.
Oh, so yeah, definitely only from the Deep Space Network. Bet. All right. So let's see. So we put forward some atomic clock measurements, right? And you were saying that this is different from the Mossbauer detection, but actually that's not true here. So let's take a look at the inner workings of an atomic clock. To be brief here, we're taking cesium, sending it as a coherent beam through collimators to a magnetic field into a resonance chamber where they're shooting radio waves at it at a specific frequency to match the resonance of the cesium gas, and then it leaves the magnetic field, gets ionized and converted into an electric signal, which they then read that energy as the whatever like pulse that makes. They're like, okay, that's 9,192 millionths of a second or whatever. So like that's how they break it down. So that's actually the exact kind of same mechanism as the Mossbauer detector. It's just converting the energy into an electric signal, which they do to take their readings. So as I pointed out, though, that the speed of light's actually changing with the vertical interferometry, as noted by the fringe displacement. So the mechanism of like, oh, this is due to the gravitational field of Einstein stuff, not even on the table with that. So all the atomic clocks are just this, like literally the same, suffer from the same issue. They're not able
Alan,
to make a distinction.
Alan,
yes.
Did you see this with your own eyes?
What's that?
That's your standard.
No, that's how they work, brother.
No, that's your standard of evidence. You don't allow anything that you didn't see or somebody didn't see with their own eyes, right? If they didn't see it with their own eyes, it doesn't exist.
Yeah.
Right?
Cool.
That's your standard, Alan. I want to make it really clear. This is your requirement. No. This is your requirement. You hand wave dismiss things that you don't like because you didn't see it with your own eyes. Then you're going to bring up other things that you did not see with your own eyes, that nobody saw with their own eyes.
Okay, well,
that's your standard. You need to be consistent, Alan.
Hey, moderator, please. I'm about to talk.
Yep.
Right.
What do you guys want to do?
So
go ahead.
I got you, bro. So the standard for evidence, right? You're talking about an optical observation to confirm the bending of starlight that no one's ever seen, right? This is an atomic clock with mechanical parts that can be measured that does specific things and functions a specific way. It's very clear how this works. There's a diagram. You can look at it. You can figure out how it works. It's not a mystery here. I'm not making a giant leap of logic. These redshift detections do not go your favor. Interferometry shows that the speed of light is actually changing vertically. So the application of, oh, this is due to the gravitational potential of the Einstein field, not on the table again, sir. And you're not going to get me with, oh, your standard for evidence is different when you're bringing up a phenomenon that no one's ever seen outside of a computer, when we have actual technology here on the ground that we could look at.
MCToon.
Do you have a response?
Yeah. People have seen it. People have done it. And you're hand wave dismissing it because you don't like it. That doesn't work that way.
Show me their pictures that aren't from the Deep Space Network.
I don't need to. Deep Space Network is perfectly fine.
All right, bet. All right, so
there's nothing wrong. There's nothing wrong with that evidence unless you actually show the error in the evidence, Alan. If it's wrong, show it's wrong. But just I don't like it, therefore I'm going to not respond to it is just waving a white flag.
Okay, I'll go.
It's not that I don't like it, right? The prediction of the bending and all that comes with specific requirements involving the gravitational field, right? On the ground, in the lab, what we can measure, what we can confirm, doesn't show the same relationship that would be applied to the sky. So if someone's sending you images from a Deep Space Network that no one's ever seen with their own eyes, and it says, oh, it matches this formula that doesn't even represent the behavior of light in reality in the lab, then what are we doing here, bro? That's the distinguishment here. It's not that I don't like it. It's that there's prerequisites for believing it that aren't substantiated in the lab.
Okay, yeah. So it didn't solve any problems, though, Alan. You just don't like it, and you just ignore it. So I will apply that standard to you. So any evidence that you bring, you need to make sure that you have the ability to look at yourself. Okay, that's fair.
Are you denying the functionality of an atomic clock? Just for the record.
No. I'm saying that you're not allowed to bring up an atomic clock because it doesn't match your standard of evidence. Because you aren't seeing the atoms moving through there, and you aren't seeing them get counted, and you aren't counting them, right? A computer's doing it. It's through some abstraction that you didn't have control over and your eyes didn't see. So you don't get to use it for your own reference. You only get to use things that are consistent with your standard.
Toon, did he lay out the difference?
No, I don't care. Watch me use it. Okay, so you believe in little counting particle atoms. That's not even what's happening, dog. They're converting a frequency, they're ionizing it, so it's just energy, and then they're turning that into an electric signal. That's not counting atoms, dog. This whole model of how this atomic clock works based off of the valence electron and all this stuff, completely irrelevant, dog. All that's happening in here is that there's gas.
What's a frequency?
Huh?
What's a frequency?
It's vibration per second.
It's a photon, Alan.
No, that's a conceptualization.
There's a photon emitted when the electron changes state. Right?
No, that's the quantum model.
Yes, that's what's happening. That's what's happening.
That's the model of the photon, right? Which is reified by the Compton effect.
None of that exists because you didn't see it with your own eyes.
Okay, well, 1 second, dog. If you're going to invoke the photon, right? So at the beginning of this debate, I said that we're going to skip over the photon because it's a complex subject, right? But if you want to get into it real quick, we can do that, okay? So you're arguing that, it's the quantization of light, there's a little particle and all this, okay? That comes from applying Planck's constant to the frequency, right? So just multiplying the hypothetical amount of energy that can exist in a second as the quantization of the part, right? Now,
No,
E equals HV, dog.
Yes,
it's literally that. So anyway, I'm going to continue now.
Yeah.
Thank you.
Good.
So H mu, right? So anyway.
Nu.
Yes. So what they're doing there is that they're just multiplying the quantization of the black body radiation from Planck's constant, right? They're saying that this is there's a proportionality ratio with the particles, right? Now, this is reified entirely, not from the double slit experiment, not from the quantum eraser experiment, not from the which way experiment, but from Compton scattering, right? We're told that this is a mutually exclusive proof of the photon, and this really settled the deal. And this is the backbone of particle physics and quantum mechanics. Now, again, you're never going to believe what suffers from the same issue with the Compton scattering prediction for the wavelength change. They're doing an energy frequency conversion through ionization to measure the energy and assuming that the output is proportional to a wavelength change that they need to reify their model. And then while they're analyzing it through relativity, they go, okay, well, we have this stationary electron that doesn't move, so it has no kinetic energy. And then they go, okay, this photon hit it. Now there's a billiard ball collision. And because there's no kinetic energy, blah, blah, blah. It's based off of all these assumptions to reify the model. I don't subscribe to that version of the photon, nor do I need to talk about the measurements that are made with the atomic clock, dog.
Yeah, well, I was just pointing out that you're not using your own standard of evidence here, but that's fine to be inconsistent. But the point of all of this is that they are accurate in their measurements.
Well, agreed. But the problem is there's no this measurement doesn't tell you if there's little tiny balls colliding or anything about the constancy of the speed of light.
And of course, that's beside the point of the gravitational redshift.
Point, because you're saying that I can't use it unless I can see all these little tiny balls.
You're saying that you can't use it. I'm just holding you to your standard.
No, you're saying you can't use it because of you're saying I can't use it because I said that
because your standard of evidence doesn't allow you to use it.
You're invoking something where the measurements don't align in the lab.
No, Alan, I'm just saying that you can't use things that don't meet your standard of evidence. It's hypocrisy. Don't you see that, Alan? No. You reject things that came from a computer measuring things when they don't agree with you, but you will accept things when it's a computer measuring things when they do agree with you. That's inconsistent.
When it's real technology that you can use right? The explanation of how it works, I don't agree with, right? But it does function that way, and it doesn't tell you anything about the constancy of the speed of light, which is required for your gravitational proof. That's the whole purpose of it. That's why, yes. Why would the gentleman from Pound Repka say, "Hey guys, we're going to need to do this with an atomic clock because we actually can't tell with our frequency detectors," and then you're going to turn around and
then people have done it with an atomic clock, Alan.
It's the same
many times,
brother. You understand the conversion of how they're making the measurement? It's this. They suffers from the same issue. You get that?
Did they measure a difference in the clock?
Yes.
Okay. What caused the difference in the measurement?
Did they measure a frequency shift or a velocity shift, though? What caused the frequency to shift, though? Was it velocity or was it gravitational
Gravitation.
potential? How do you know? Ta-da!
Yeah. And how do you know that it was frequency or velocity?
Interferometry.
Where?
The fringes wouldn't be produced if it was.
There's no fringes in these.
If they were in phase. But the evidence that I invoked, right? Remember how we came with our own evidences? And I came with vertical interferometry that showed a fringe pattern. 3 separate people confirming it. One of the dudes was a guy that was against it, right? He made his device. Yeah, hold on a second. Hold on, dog. One of these guys. He was like, "There's no. This isn't real. This is a mistake. Instrumental error. Blah blah blah." He does 2 iterations of the experiment after making improvements on it. Measures the same thing twice, dog. So we have variance in the speed of light vertically, hands down. So my evidence supersedes yours. Yours is a frequency shift that can't determine anything about relativity or classical physics. I have the actual determination factor here, buddy.
All right, that doesn't at all apply to the specific one that I brought up.
Yes, it does. Does what you brought up involve electromagnetic radiation? Yes, right.
Yeah.
So it
they're measuring the base state between electrons and strontium atoms.
Yeah. Well, luckily we could measure the propagation rate of that too to see if it's going faster in one direction than the other, and it shows through interferometry that it does.
Alan, how can the speed of light vary when the number of photons is what they're counting?
They're not counting the number of photons. It's an energy conversion based off of frequency, right? So they're not counting photons. You have a gross misunderstanding if you think an atomic clock is counting little billiard balls.
Well, photons aren't billiard balls.
Well, conceptualization of them would have to be, right? Because you're counting a little something that's not nothing, right? So what are they counting?
They're not.
Right?
They're not. That's not the idea of what electrons are or what photons are.
Well, we already went over that,
but
like I said, we're doing the simplification of it. Okay, so the nothing hits the photon, or hits the electron.
It's not nothing hitting it.
Listen, guy, you're the one. It's just a joke, man, because you're like, it's not a billiard ball, but it does an elastic collision involving a little tiny sphere. I don't know. If you want to call it not a ball, that's fine. And get into the semantics of it. You're the one that believes in the quantization of light, not me.
All right.
Okay. Time. And then we go to another topic. Is that right?
Yeah, I think I present.
You went. Yeah, you can. You won the toss. So he went first last time. Now you're going to go first this time.
Yeah.
Gotcha. Okay. So you got 12 minutes when you're ready.
All right. I'm going to share in just a second.
And okay. Whenever you get started, we will start.
All right. You got that there?
And you're sharing screen?
Yep.
Okay. Whenever you start.
All right. So I'm talking about light deflection or gravitational lensing. The Allan went over this pretty well. The hypothesis from Newtonian with the mass energy equivalence is that light passing near gravitational wells will deflect. And the general relativity hypothesis is that light passing near large gravitational wells will deflect twice the Newtonian amount. And of course, the null hypothesis is no deflection, or different people have had different interpretations over time. So this is a diagram to scale of what is going on here. So we've got the Earth there on the top right. You've got the source and the sun. So the source is the light is going from the source to the Earth, and the bending. There's no bending in this diagram, but the bending will cause the light to appear to be from the reference source. I use this one because it's got the variables listed on there. So it's important here to look at. This is a little bit of math in this one here. We've got delta theta on the bottom there. That's the change in the apparent location. Is 1/2 of 1 plus gamma. So that 1 is the Newtonian deflection. If you remember from the previous one, the hypothesis for Newtonian is is a particular amount of deflection. That's the 1. And then we've got the gamma, which is the curved space-time deflection. So you got 1 plus gamma. Gamma in this instance, if general relativity is correct, then it's 1 as well. So you've got 1 plus 1 is 2. So you got 1/2 of 2, which is 1. So when you multiply that by everything else, you get nothing. It doesn't change, not nothing. It doesn't change it. It multiplies out to be just 1. You've got 4 times g times m, the mass of the sun, over c squared d. That is, on the right, we've got the little key there. The important part then is also 1 plus cosine of phi. And phi is the angle between the sun and the path of light that it took, over 2, right? Now, when for the limb of the sun, which is so a grazing ray that comes right next to the sun, phi is 0. So the angle between the sun and that light there, and that from the source on the bottom left of that diagram to Earth on the bottom right diagram, that the distance between the sun and that ray is phi is 0. Cosine of 0 is 1. So that total right term is 1 plus 1 over 2. Again, you get 1, leaving all in the middle there 4 gm over c squared d. And we'll see that in the next one here. But the prediction according to general relativity is 1.7505 arc seconds at the limb of the sun. So here's the two predictions, the Newtonian prediction and the Einstein or general relativity prediction there. We've got theta equals 4 gm over c squared r, and that's the same one here on the top. 4 gm over c squared d. D and r, different variables, different papers reference them differently. Anyway, so that's the hypothesis on the edge of the sun. Here is the graph of what they would look like in relation to the distance that they are from the edge of the sun. On the left vertical axis is the deflection in arc seconds, and on the right is the solar radii. So at 1 solar radii away, you've got a deflection of 1.7 in that red and 0.8 in the blue, and then the horizontal axis of 0, that's the null, where there's nothing predicted. So there's a null. All right, so the Eddington plate, yep, there are plenty of issues with that, and fortunately people have done better experimentation since then. So again, here is the one from Don Bruns, where he controlled for confounding variables very precisely. This you see that paraboloid there in that diagram? That is the light, the wave front of the light as it passes from the lens to the plate of the sensor. It's out of scale, but he's using the positions of different stars to measure how much that modifies it, and then quantify that so that he knows exactly how much it's deflecting that, so we can do that, get some precision. The important thing about this is that he did it in 2017 using consumer level equipment. You can do this yourself. In the past, it was stuff that people, it was difficult to do because you had to have some pretty big equipment, but now you can do it yourself. These again are some of the pictures he took. And here is the chart of the displacements that he took. You can see the black line, I believe. I'm colorblind, but I think the black line is the Einstein prediction. The grayish line there is the Newtonian one. Of course, the horizontal axis is the null prediction, and these are the positions of the stars. Now you can see how far out he measured them. This went almost to 5 radii out in his, and his results were within 3% margin of error. Here's his conclusion, an uncertainty of only 3%. So that's the most recent optical measurement. But there have been radio interferometry measurements since then. In 1976, Erwin Shapiro figured out, no, it was 1960, forgot the year, 1967? I think I wrote it down wrong. Erwin Shapiro figured out a precise method using radio telescope interferometry with multiple telescopes that are distance apart. The farther apart they are, the more precise they are. It's called VLBI, or very long baseline interferometry. So if you see VLBI, that's what it is. This is a chart of the different measurements of light deflection over time. that bar across the middle there, 1.0, that's gamma equal 1.0. That's the prediction of general relativity. And so you see at the 1973 expedition to Australia, the final eclipse, one put on by a large organization. And you see those error bars, they're rather large. And then in 1974, the radio interferometry from two quasars is significantly closer, and the error bars are much tighter. And since then, there have been several others, much more precise measurements. So here is the specific one from 1974. Shapiro was involved himself. He's one of the authors on the paper. They used the 120-foot haystack radio telescope and the 60-foot telescope in Westford, Massachusetts. They also used two 85-foot telescopes at the in Green Bank, West Virginia. And here we see after their they tracked two quasars as one of them passed into the sun, and they were about 10 degrees apart, and they were constantly measuring the deflection between them. And they started quite a few degrees out, not much more than, or they were more than 8 solar radii out. I think they were 15 degrees out from the sun in this particular one. So again, their results are gamma equal 0.98 plus or minus 0.06. That tracks with relativity. And again, you see that gamma is the Eddington, I didn't mention Eddington-Robertson parameter, or general relativity, equals 1, and that's the equation again. I'm reminding you of the equation because that's what they're always testing here with this gamma stuff. Since then, there have been more. This is from 2004. This is a different Shapiro, SS Shapiro, not II Shapiro. Maybe they're related. So the experiment used 87 VLBI sites, 541 radio sources, yielding a total of more than 1.7 million ionosphere corrected group delay measurements. So 1.7 million measurements. So where Eddington had 7 and Don Bruns had, I think, 17, they had, this is 1.7 million different measurements into this study. Here is the positions all over the Earth of where these radio interferometer radio telescopes were located. And this right here, Allan, is the one I was talking about. You can see here the distribution of the positions of the measurements in relation to how far away they are from the sun. And even at 175 degrees away from the sun, the amount of deflection due to the gravity of the sun is 2-digit milliarc seconds, I believe. And the precision is significantly more than that in this type of measurement. So they're well within their ability to measure even 175 degrees away from the sun. So this big arc of measurements in the middle is not the actual measurements, it's the number of measurements that they did in relation to how far away those measurements are from the sun. So 1.7 million measurements right there in that graph. And that power graph there on the top left there, you see that? Arcing down toward the bottom right. That is the Einsteinian prediction, gamma equals 1. That's what that line means, is gamma equals 1. So what were their results? They got 0.9998 plus or minus 0.0004 of gamma. So gamma equals that. It's predicted to equal 1. So they're within, that's 4 times smaller than any previous measurement of gravitational deflection. And again, I put that, the equation on the screen there again. Gamma is the Eddington-Robertson parameter of general relativity. If general relativity is right, it equals 1. They found it to be 9.9998 plus or minus 0.004. So 1 is within their error bars and is very, very precise. And they did definitely get farther away than any plasma corona of the sun.
1 minute.
So anyway, in conclusion, we got multiple different lines of evidence. I didn't cover other ones, but there are other measurements as well than just radio interferometry. They've used quite a few different techniques, including Shapiro delay. It's a different way. It doesn't need 2 telescopes as much. Using varied methods, they've measured deflection. These confirmed a high precision that light deflects into gravitational field, the amount predicted by general relativity. So there you go.
Okay, I believe you are supposed to ask him a question now.
Yes. I don't know. I don't have a question for you, Alan.
That's
I got you, Brody. So I'll throw you a bone. So I'm not disputing the phenomenon of displacement. I'm disputing the causal mechanism, to be clear. As when shown in the lab, the gravitational field, which is assumed to be the causal mechanism, doesn't seem to hold true, nor does the interpretation of light, being that it maintains a constant speed, which is required for the interpretation. And then we have, let's see. So again. So this is the equation, though. It's still just a ratio, so it's not telling you anything different than the plasma lab. They're still making the exact same prediction. So when you get to the displacement outside of the solar limb, like again, that is interesting, but with the causal mechanism is in dispute. And what I would like to turn it around to you and say is I would like to point back to what Silverstein said at the November 6th meeting at the Royal Astronomical Society regarding the eclipse, where he says if there's no substantiation of the redshift to match the displacement, we can't attribute this phenomenon to Einstein's laws of gravity, because if there's no curvature from the gravitational field, then that's not, that's not the causal mechanism, and the theory can't explain anything because geodesic paths would just be straight lines with no curvature to travel along. So do you have anything to say about that?
All you did was deflect to a different topic. Let's stick with this topic.
Well, your topic requires a causal mechanism, which again, I'm not disputing happens, but it's the causal mechanism associated with it, right? Because there's like not trial and error. Like when you're doing science, you're establishing a cause and an effect, right? So we see a phenomenon. Oh, there's a starlight displacement at a proportional ratio regarding the speed of light and the radius, and these are constants that we apply to it. So it's like, what does that? Is it a gravitational field or is it something else? How do we know? Well, we can test in the lab the concept of the gravitational field through the frequency readings like we did earlier, right? And through interferometry. So we can determine how light's functioning here on Earth in the expected gravitational field to see if that would be applicable to the sky. And it turns out it is not.
You didn't address the topic at all, Al. You still didn't.
The phenomenon
you said
causal mechanism. They're hand in hand, bro.
Your guy that you brought up, what was his name? Dowdy. You said it's in the limb. For the audience, what is the solar limb?
The solar limb is just at the edge of the sun, where space meets the sun, essentially, right?
Yeah, okay.
Where that light stops.
Yeah. So you said that when you talked about it, you said that they've never measured deflection outside the limb.
I wasn't aware of the other ones that you brought forward, but I have.
So now I showed you measurements outside the limb.
Yes. And the predictions are still in alignment with the same ratio, but there's supposed to be a causal mechanism established with it, right?
But you're claiming that it's refraction in the atmosphere of the sun. That's what Dowdy was talking about, right?
Well, I'm not specifically claiming that, but what I'm claiming is that using that ratio, you can come up with different stories about why it's displacing.
Okay, and let's hear them. Let's have the empirical evidence supporting them. So far, it's just an appeal to possibility.
Well, that's what the theory of gravitation is, right? It could be it could be space-time curvature, or it could be some other mechanism, right? Because if it's
you're proposing something else. But let's have it. What is that other else? Where's the empirical evidence for the other else thing you're talking about?
How do we determine which one is which, right? We do the lab experiments.
Alan, there is no sun atmosphere 175 degrees away from the sun.
I don't think you understand what's happening.
So your Dowdy reference doesn't apply. So I'm asking, why is the light deflected the amount it's deflected? And you don't have anything. Dowdy doesn't apply.
Dowdy's thing still applies. His equation doesn't stop at one solar radii, homie.
He said that it is happening because of refraction in the sun's atmosphere. There is no sun's atmosphere 175 degrees away from the sun.
Listen, dog. His equations make the same predictions. Your equation, to substantiate it, to be associated with...
a
Don't interrupt me.
mechanism.
Don't interrupt me when I'm talking. So, to substantiate your theory as the causal mechanism, right? There has to be an associated amount of frequency shift, right? The light has to be retarded proportional to the magnitude of the gravitational field. Do you understand that?
Yes, and it has been empirically confirmed.
Okay. It actually hasn't, though, because as we just went over the history of it all, it's all based off of converting a frequency of energy into electric signals, which doesn't tell you anything about the wavelength or anything about the speed in which the light was traveling, right? So to falsify that, you would do it with interferometry, and that's already been
falsify
done.
it, you would need a measurement of that light then, since you think it's light's speed that's changing instead of the frequency that's changing.
It's
right?
You don't know how an
claim.
interferometer works?
We do.
That's exactly
but
what it
this
measures.
isn't an interferometer.
It doesn't matter, dog. It's electromagnetic radiation.
It does matter. You're talking about an interferometer when we're not using an interferometer to measure it.
What's the speed of electromagnetic radiation?
What's the speed? It's the speed of light in that medium.
Okay. What does an interferometer measure?
It measures... it doesn't measure the speed of light.
What produces the fringe pattern that's proportional to the velocity that it's measuring? It's a variance in the...
It's a displacement.
Based off of what?
And many things
what
can cause
it?
a displacement. A difference in the path can cause a displacement.
You say many things can cause a displacement.
A difference in the length of the path can cause a displacement.
And what causes that? Is it a proportional relationship?
Movement can cause it.
Is it a proportional relationship with the velocity? Yes. So the measurement shows that in order for there to be a fringe, that the speed of light has to change. Now, the path length in reality doesn't actually change, nor does the time, because
of course the path length changes.
Hold on 1 second. Don't interrupt.
When it's moving.
Listen, dog. Conceptually, right? You can make a prediction in a lab frame using the formula for the displacement based on the velocity of the rotation of a table, right? And then that plays out on the rotating table. The time and distances are exactly the same, and the ratio of the speed of light is produced.
But they're not the same, Allan.
No,
if the distance is not the same. While the light is moving, the table is also moving, and the path changes in length from when it's emitted until when it's read.
So number one, you're invoking absolute space to change the distance of the table for yes, you are for invoking or for electromagnetic propagation. Now, if you do that right to maintain the speed of light,
I'm not.
Yes, you are. And I'm going to explain.
Tell me I am. I'm not.
I'm about to explain how.
The path changes length.
Explain how you are. Please don't interrupt. So this is how you're doing it, right? If the speed of light is the same, and it's the table that's causing the actual displacement, then there would be no fringe pattern. It would recombine and not produce a phase shift, right?
I disagree completely.
You can disagree completely.
I completely disagree, and I'm 100% not the fringe person here, Allan. While the light is moving from the emitter to the receiver, the path can change in distance depending on the movement of the apparatus.
Conceptually, if you invoke absolute space, sure.
No, you don't need absolute space to do that.
100% you do. That's the whole point of Einstein's theory, and
there's no absolute space in this at all. There's an emitter, there's a receiver, there's a path that the light takes, and if the light takes a different path, one direction and the other direction, and the length of that path changes, we don't need any absolute space to do that. They're all relative to each other.
If the speed of light is the same, it won't recombine and produce a fringe, though, right? So that's a problem. So anyway, we can move on from that, though, because
you don't like that? All right.
No. I mean, we can stay on interferometry. The purpose of it was to be more in talking of frequency shift and stuff, but I guess we can't really move on from it because it's the crux of the two differences. So if you want to get into how interferometry works and the exact mistake you're making, we'll look at this right here. So
you have your 12-minute response still to go, right?
Perfect. Oh, do I? No. Okay, great. We're about to learn about interferometry.
Okay. Do you have any final comments on that one, or we'll let him know his response?
I guess we will shift topics. All right.
Well, we did your 12 minutes, and then you didn't have a question for him.
Yeah.
So we were kind of just in la la land.
Yeah.
All right. So now you got your 12 minutes. Go right ahead.
1 second. All right, so this is let's see, 2022, so a recent one. Now there was one in 2015, but this is the modern one. So exactly how Toon was describing or misdescribing how an interferometer works in regards to absolute space and the time being different due to the rotation of the apparatus, that's actually not true. That absolutely would not produce a fringe, and I highly recommend everyone that thinks it would produce a fringe read this paper by Barreda and others, 2022, who's going over the Sagnac effect and how it's difficult to explain through relativity, because if you would do what Toon's doing there, saying, well, the distance is changing because it's rotating, that's invoking absolute space, it cannot produce a fringe. This entire paper is about, hey, we can explain this without using a Lorentz transformation, but they can't. It can't be done. It's literally C over V, or I'm sorry, V over C. There's a ratio relationship with the velocity. That's what produces the fringe, and it's proportional to velocity because the wavelengths are not combined at the same time. If the distance was actually changing and C was the same, there would be no fringe measurement. It would recombine with no fringe. So that's not even on the table, right? Now, that's really all I needed for that. Okay, well, real quick, we'll go to Einstein. We'll see what Einstein has to say about absolute space and this exact problem right here. So here we have Einstein, oops, it's the wrong year. There's my 1905 Einstein. 1 second, lads. On the electrodynamics, moving bodies. That's weird. Shoot. Okay, well, anyway, Einstein says in his 1905 paper in the first 2 pages, right, he says we don't need an ether, so we don't need to invoke absolute space, and we don't need to describe or ascribe imaginary vectors for electromagnetic propagation where none such exist. And what Toon's doing there by just changing the distance of it, he's invoking electromagnetic propagation in imaginary vectors where it doesn't exist, right, to maintain the constancy. So Einstein's like, we don't need that, we can explain it without it. So this is an explicit violation. Later in the paper, he goes on to say that his equations hold true in any uniformly rotating polygonal circuit. So if there's a closed light beam in uniform rotation, now they say, okay, that's an acceleration because it's rotating. Any point from it will be infinitesimally, accelerating that are different from the last, blah, 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 right? But what the actual implication is, right, is if you take a closed polygonal circuit and extend it to infinity, it doesn't really deviate from linear motion, right? So it's identical. So he's saying that his equations will hold true in that frame. So when you apply a rotating interferometer, the speed of light should not produce a fringe, and it does. This is why Sagnac said in 1913, when he released his mixtape called Ether, that he falsified relativity theory. All right. So I think that's all we need to do to cover the conceptualization of light. Okay, yeah, one more thing. So in relativity theory, they say that there's no frequency shift that there's no change speed in light. There's no velocity change. It's a fixed velocity, and that when there's a frequency change, right, when there's retardation, light's not slowing. Well, the frequency is slowing, but the wavelength is extending inversely proportional to the frequency shift to maintain a constant speed. But that's actually not what's happening, and we can show that through interferometry. So when we look at the atomic clock, the humble atomic clock who's converting signals into electric or converting energy into electric signals, that's not telling us anything about the causal mechanism of the shift or the behavior of light in a meaningful way that can be substantiated, that would be required for general relativity to be proof. And here we go. I got a little screenshot to pull up here. So here's from Einstein's paper here. And I already covered it, so we don't need to reread it, but it just says light is always propagated in empty space with a definite velocity. Its C is independent of the state of motion. Now, obviously, we're talking about a place where there's a medium. You can account for that in the equations. It's not the concern here. The main priority is that the speed of light is supposed to be the same. And if it's not, and if it's producing fringe shift patterns proportional to velocity, then there's something else going on, because when you do the equation V over C, you're referencing light in its inertial reference frame, which is absolute space. Good game, lads.
Okay, Toon, you got a 1.5-minute response.
A 1.5-minute response?
You can respond as long as you like.
You can respond as long as you like.
The question and answer part of it, I think, was a little we kind of misinterpreted having that in there still. Maybe we just go to the open.
Yeah.
Okay, we can go to the 12-minute convo.
Okay.
Yeah, absolutely.
And just try and let each other finish if you could, please. Thanks.
Yep.
Yeah.
All right. So, hold on. Gotta fix this.
Okay, these are good. I'll set the clock for 12.
All right. So here you go. Here is interferometer. You got light comes in, splits, goes two directions, gets a little simplified. They go around a few more times potentially. It comes out, and if it's stationary, then the path here and the path here, same length. Here you go. A moving, rotating interferometer. Light comes in here. While the light is moving through the interferometer moves, and then when they're recombined, this path of light had a longer path, and this light had a shorter path. So they're going to be out of phase with each other. There's no absolute space in there. It's all completely relative to where it started and where it ended. That's how an interferometer works in relativity. I don't know why this is a difficult thing. So.
Okay, so let's see. We're going to look at now what we have here is a paper by Niklaus and others where they're explicitly talking about the Sagnac effect, and they go over 22 different iterations of people trying to explain it through relativistic confines, making the exact mistake that Toon is currently making right now. So the speed of light is not the same, and it changes proportional to velocity, or at least that's what the recorder makes. Otherwise, there wouldn't be a fringe pattern. So all these lads right here, so 14, 25, 28, 10, 20, all these people, right, are all trying to explain why there's a fringe shift pattern when there shouldn't be, right? Now, they try to explain it through, they say, okay, well, it's uniformly rotating, so it's an acceleration, so special relativity doesn't apply. We got to apply the general theory. Why do we do that? Because we can convert the energy, we can conserve it into a gravitational field, which generates little temporal pockets of link contraction and time dilation, right? But that's obviously insane. So the way that they go over it now, the way that they teach it to people so that they don't understand it, and they talk about it the way that Toon just did, is they show you they talk about it like a time displacement. They'll say, well, we'll invoke a geometrically convenient position. We'll put an observer at the center of the rotating device, and compared to an observer at the rim of the device that's rotating, this will be the time differential. So earlier when we looked at the graph that explained space-time separation between an observer in motion and a stationary observer, this is what we're looking at, right? This is what they're invoking to explain it, right? This is what this whole paper is based on. Let's see, ether critiques. So it's Artiglia 2015. This is what they're talking about. This is what they're going over. They're doing the same thing. They're setting up their geometrically convenient position to talk about it, but they can't explain the actual fringe, dog. It's literally not how you said. Otherwise, the technology wouldn't produce a fringe shift, right? The best you could get would be a second order Doppler shift. You wouldn't have a physical displacement that you could measure that would be proportional to the velocity, right? All right, so that's...
Well, I disagree, dog.
Noted.
We should stay on this and see if we can get to the bottom of it. I mean, we shouldn't have a disagreement about this item.
It takes time. It takes time for light to travel. And the apparatus moves during that time, and one of the paths is shorter and one is longer. This is, I don't know what this paper that you're talking about has any problem with. This isn't that difficult to understand.
Yeah, these are the mainstream explanations of people trying to explain what you're doing right now and holding it up and going, "This is so easy, guys. Why don't you get it?" Well, yeah, you should go tell all those guys. You should go tell all those guys.
I don't care about those guys. I don't know why they don't get it either. I don't know.
Maybe Allan, explain how you also agree that those things get there in different time and how that's maybe help them out there.
Okay, so yeah, light will be measured differently proportional to the velocity of an observer. Okay, and that's the way that every other wave is measured, right? They say that light is special and that it's independent of all this, right? So when they tried to apply this to their equations and everything, they were like, okay, we can do all these kinematics to it, and it's all nice. And then Sagnac came along and showed that it doesn't function that way, right? Because if it did, there wouldn't be a fringe displacement. There wouldn't be a gap in the light. It would recombine at with the same phase, right? There would be no displacement to be proportional.
Well, why would there not be? When one of the paths is longer than the other, they're going to be out of phase with each other.
Because they're traveling the same distance though. And the speed
they're not
of light,
traveling the same distance. One is traveling
speed,
longer than the other because the apparatus moves while it's in flight.
If the speed, dude, it goes in both directions, dog. You know that?
Yeah, and one gets shorter, one gets longer.
And if that happens and the speed of light's the same, what happens when it recombines?
Then they're out of phase with each other.
No, they'll be in phase with each other.
Why? Because the one had a different path than the other.
No, they both complete the same distance.
No, they don't. They have different distance that they travel.
Yeah.
Unless it's stationary. But if it's moving, then while the light is moving through the apparatus, one has to take a longer path than the other to get to the point where they mingle.
I got you real quick. So let's see. I think I see where the confusion's at, bro. Let's see what we can do here for you. 1 second. Okay, so we have here the old Sagnac equation, right? Delta T for omega A over C squared, right? And we have the linear version, delta T 2VL over C lambda, right? So in this equation, right, you do this in the lab frame. The lab lad will fill this out, right? He's going to make a prediction based off of a rotating device. And then what's going to happen is that device is going to rotate. There's going to be a displacement based off of this information right here. So when the device is stationary and the area of the device is fixed, right, and the rotation rate is fixed because they know how fast they're rotating it, the area
zero.
The area doesn't change, and when it's rotating, the area doesn't change, right? The lab frame prediction and the prediction on
omega is the motion. So when it's not moving, omega is zero. The whole equation turns to zero.
Right. Yeah. So listen though, dog. This equation doesn't. There's no like separate interval where they're like, okay, well we have to account for the displacement for the rotating observer or anything like that, so that there's going to be a different so that this area changes, right? They're the same prediction.
Change. Omega changes.
Doesn't matter.
Why doesn't it matter? It's right there in the equation.
The distance stays the same, dog.
No, it doesn't.
Yes.
The distance is different, and your linear version does the same thing.
And what happens to this? And what is the speed of light doing? Is it traveling the same speed while this is rotating or not?
Yes, it's traveling at the same speed.
And
since it moved in the process, hold on, Alan. While it was moving at the same speed in both the paths, the distance changed. One path got longer, the other path got shorter. The point where they're recombined moved toward one of the light paths and moved away from the other light path.
And if they're moving at the same speed, they would recombine, right?
Because you can determine how long it takes light to travel based on the path length. It's a simple part of the equation, right?
Where in the equation is the change in path length noted?
It's not in this equation.
Where's there a different area?
Where's there a different area?
It's not.
The area is not changing, Alan.
I know.
Area is the same.
I know.
It's the rotation.
And you need to understand that. Because if the speed of light's the same, and if that's rotating and it recombines, then there's not going to be a fringe displacement, dog. So it only works if it's measuring a variance relative to the velocity, dog.
Light is consistent at this in both reference frames, and one reference frame is longer, and not one path is longer, and the other path is shorter, then they won't get there at the same time.
You're grossly arguing against special relativity by invoking absolute space to even do this.
No,
bro.
There's no absolute space. It's all relative, completely relative. There's no absolute space here. I didn't reference absolute space. There's a relative difference here and a relative difference here.
You see it? It's right here.
The speed of light is not absolute space, Alan.
Velocity, right? Ratioed against the speed of light.
Within the reference frame, Alan.
What's the reference frame of the speed of light? Is it the ether? Is it absolute space? These are the exact concepts that they were talking about all these years ago when they were doing this, right? This is a complete falsification of relativity theory. And
all you're doing is you're repeatedly saying that these different paths are the same length somehow. That's what you're saying. That these different paths are the same length. That's what you're saying, Alan, right?
Relative to what?
To each other.
To each other, dog. All right.
They're relative to each other, different lengths, right? Yes or no?
No, they're the same length, dog. What are you talking about?
Different lengths, Alan. Why are you saying that's a different length?
Wait. Do you bet. So you think that it recombines at a different spot like that? Like what the like? I don't understand. Like
the place where they recombined moved since the light was emitted.
But the speed's the same, so I guess it caught up in time just to make not a fringe pattern. So anyway, we've got 2 minutes left.
They still have a fringe pattern.
No, it wouldn't. So we're going in the biggest circle jerk ever. I think we both said the same thing that we need to. We could move on to another subject now if you like. I'm not interested in.
Yeah, I'm not sure we'll get anywhere.
Yeah.
There. Whatever topics you want.
How does an interferometer work, Alan?
It splits a light beam and it recombines after completing a circuit.
Okay, and then why is there a fringe pattern?
Well, so there will be velocity, right? And that causes the fringe shift pattern to be measured, right?
What's causing a different velocity?
The motion of the apparatus.
Okay. But I don't understand why a consistent speed of light and a moving apparatus, it doesn't work for you. Why do you think that's a problem?
Because it would complete the circuit at the same time on both sides and not produce a fringe. Yes.
No, they wouldn't. One got longer.
Nope.
I don't see why you think that that didn't get longer.
Mm-hmm. I mean,
why? I mean, this diagram do you not see that this one is shorter than that one?
Yeah, I can understand like what you're saying.
Okay, and there's an amount. And there's an amount of time from when they're split until they're recombined. There's a delta t in there.
Yes.
And during that delta t, the apparatus is moving.
Yes, they do describe it with a delta t, but the delta t cannot describe the actual fringe pattern displacement, dog. This is part of like the confusion for it, and especially with removing the general relativity explanation and putting it back on a time displacement, like as if they're accounting for it with special relativity when it's explicitly not, right? So all these gentlemen that we just went over, all the modern papers that still can't explain it, they can't explain the linearization of the Sagnac effect, but
I just explained it. Amazing. And the linearization was also explained. It's pretty cool.
Interrupt me. You, while invoking absolute space, have not explained a single thing, and you've gone contrary to relativity theory.
I mean, I'm just right in line with it. I don't know why you're saying that.
Are we confused whether or not the device is moving itself? Are you? I guess that's where I'm confused.
I don't know.
Or are you saying that the Earth is moving, causing that displacement? Or are you saying that the device itself is?
He's saying that the distance of the device is changing as it rotates, which you could look at it that way, right? But that's invoking absolute space, which Einstein explicitly says.
No, it's not. It's not invoking absolute space.
Listen, guy, don't interrupt me because of your lack of understanding. If I'm talking, just sit there quietly and laugh, okay?
Right? The condescension comes out, Alan. You don't need to do that, dude. You better.
You've been doing it to me a lot, and I'm trying to talk, and it's frustrating. So if I get a little condescension with you, just mute your mic and sit there and smirk, okay?
Alan, go ahead. You guys want to go to your closings? Or you still have more to talk about?
Yes. I got you on the closing, dog. So for my closing, I would like to show that no substantial mechanism was provided to substantiate that relativity theory is the correct interpretation of the behavior of light or gravitational effects, and that or the motion of celestial bodies. It all turns out to be kinematics in the lab frame where you can actually do measurements. You can show that there's a variance in the speed of light which produces a fringe shift pattern, and that would not be possible if the distance and time were changing as noted, or as they're trying to denote, right? And I think that's about it.
Alrighty.
All right. Well, I showed that there are many millions of measurements of the shift in the light, the light deflection going all the way out to just underneath 180 degrees from the sun, consistent with general relativity. And Allan did not provide a plausible mechanism for why it happens. The Dowdy version of it is that the sun is causing refraction, but the sun's clearly not causing refraction that far away from it. So anyway, thank you very much, Allan. Sorry if we got a little hot there, but
no worries.
It's good. It's all good.
All in good fun. I think
much
it causes
appreciated.
people to go out and have to do more looking into things so that they understand it better, because I may be more confused than coming in here. So that's never a good thing. Let's see here. We're going to get to Super Chats right now, so get those in. You can either go to Rockton, send them in if you have a question for Toon, or Allan, and we'll get to those right now. Did you guys see Bill Nelson talk about the dark side of the moon? It's pretty funny, just for laughs.
Is he in Pink Floyd?
No, Bill Nelson is the head of NASA, and
but how's his saxophone playing?
What?
How's his saxophone playing?
Does he play saxophone?
I don't know, but one of the guys in Pink Floyd does.
Well, this guy Pink Floyd probably knows more about the moon than the head of NASA. That's all I'm saying.
I don't know what you're talking about. What did he say?
Yeah, I'll play it for you. Here we go. We'll listen to this. This is just real short, 44 seconds.
Are going, you think, on the backside of the moon? Do you have any insights in that?
I can't really hear it.
Sorry, I'll try
to have a lander on the.
So he's asking about China going to the moon.
What's the Chinese are doing? You think on the backside of the moon? Do you have any insights in that? They are going to have a lander on the far side of the moon, which is the side that's always in dark. We're not planning to go there. And why not? And what's the benefit of doing so? We don't know.
Just say he made the faux pas about calling the backside of the moon that it's always dark.
Yeah, but that's his reason why NASA's not going there. It's always dark. We don't go there when it's always dark.
Yeah.
He's the head of NASA.
Yeah.
Just saying. At least flat earthers know the model. Now they can say they know the model better than the head of NASA. It's kind of funny. All right, we're going to Super Chats. Let's see who we got. Let me bring you guys back up on screen. Good old Bill Nelson. He's supposedly been to space, by the way. So he says. Let's go with this screen here. See if we've got any. Thank you guys for your support. Let's see what we got. We've got. Oops, that's not the right one. Fan funded. There we go. All right, we've got up first. Let's go, Dad, says James Brown. Let's go, Dad. All right. Anybody get that one? I'll get it. How about we've got MPE. Thanks for being a member for 18 months. We got Justin Johnson gifted 5 memberships. We've got LJ for $2 says, why wasn't the lunar lander ever tested on Earth first? Assuming that's for Toon.
I don't know why you think it wasn't tested. Of course they tested it. But what kind of testing would you think that they did not do that they should have done? Maybe Jaron can suss out what he was thinking about.
Well, probably because the lunar lander wasn't made to be on Earth, is my guess. But they did test a version of it, right? That's the one.
Yeah. Do you think they could test that it holds pressure by putting it in a? I would
assume that they did that
vacuum chamber. I don't know if they did or did not. I'd figured that they probably did, but
I would have the same answer.
I would do it if I was in charge.
Yes,
but I don't know what other testing you specifically you might think would happen.
I don't know. All right, I don't know what he meant by that, but we've got Sharon is Karen. Thanks, Sharon. Thanks, James Brown. Thanks, Dad. Again, we got Eugene Austin says, McToon, did you really just say the words? I don't think you've read up enough to Allan. He literally has segments on his channel specifically for reading. My boy probably reads more than you breathe.
Well, Allan did confirm that he had not seen the one I was talking about.
Okay. We've got Wits Gets It.
It's on my website, mctoon.net. Just search for deflection. You'll find all the papers I was mentioning.
Okay, we got Wits Gets It. $5. Thank you very much. Says, yikes, Toon got completely washed. Shout out to Allan. Hey, Toon, can you attribute physical properties to conceptual abstractions? Isn't that reification?
No, that's a straw man. That's what that is, Austin. Thank you, though.
Okay, thank you. We got Upside Down Guy. $5 says, Toonies, how can we confirm the sun is not 4,000 times as big and 4,000 times as far as the moon? Or 4 times as big and 4 times as far?
How can we confirm that? Well, multiple people have measured the distance to the sun. I could go over that, but I don't think you want to go over that right now. But you can bounce right off of it and time it.
Okay.
One way.
We've got Upside Down Guy again. How close would a space pirate need to be ejected out in an airlock? Sorry, let me try this again.
Oh, that sounds fun.
How close would a space pirate need to be ejected out an airlock for a fart of theirs released in space would be pulled back to Earth?
For their fart, or for them to use their fart to propel themselves back to Earth? I like that part better, but I think they're talking about the fart going back to Earth. But if it's inside the gravity well, of the Earth, it's going to eventually those methane particles will mostly find their way back to the Earth, unless they aimed their butt away and pushed hard.
Okay. One of the dumber things.
I love that question.
I guess. Toon, can you, just for me, I like to give it a little question. Do you think E equals MC squared is smart?
Yes, it's smart.
And can you explain it for us, just as dumbed down as possible?
It is the mass energy equivalent. So, and this goes right to, I was going to talk about this, but I left it out. Too much math, but it's the mass energy equivalence of light, that even though light is massless, it has an equivalence to it. Therefore, it is affected by a gravitational well. So a single photon of light has a frequency. That's the, you can determine the mass of that. And so E is energy, but E is also h nu. So you can plug that in. You can actually get the mass of equivalent mass of a photon.
All right, sounds good. Anything? Oh, Rockfin. Sorry, one more time. We're almost done. Almost out of here. I forgot about one other spot. Let's check out who's in Rockfin. Thank you guys for being here. Appreciate it. We've got a couple. Let's see what we got. How about Fishhead Montana says for Toon, where exactly does Allan's interpretation of the fringe shift fall apart, and what is your explanation for that shift?
I think we got into that though, didn't we, Allan?
We'll see if you can answer the question as place. So where exactly does Allan's interpretation of the fringe shift fall apart? Well, I guess you've explained that. You say it moves. Okay. And what is your explanation for that shift?
Yeah, my explanation is that, it moved while the light was moving through the apparatus. And I think Allan is saying that the speed of light changed because the apparatus has a speed that it pushed to it, when it was moving or something.
So right? I guess where I'm getting lost is that I know that they measure the interferometer on a moving Earth, supposedly, and then also they tried to move it on a platform, right?
Yeah. So
do they see the same thing in both cases? When they move it on a platform, do they get the same result as when they do it on Earth?
It depends on the precision of the interferometer, right? You need a higher precision interferometer to measure the Earth's rotation than moving it quickly yourself in a lab.
Yeah, I guess where I'm confused is you're describing it as it moves, the path changes. So what is that measuring then? If it's moving, that's the reason for the fringe shift.
Yeah. So the faster it moves, the more the difference in the arrival time of that same frequency, the same photon, right?
Yeah,
that's how I thought it was.
Their interpretation of it would be like for a stationary interferometer on Earth would be that it's Earth's rotation that's doing it, and they're measuring. So they don't invoke absolute space for linear motion, right? But they do for angular. So they're saying they're measuring like a finite rotation point, and that intersects in the middle of Earth at 15 degrees per hour, right? So that's how they would attribute it to it. But it doesn't tell you if the Earth's rotating or if there's an ether, wind, or sky that's rotating. But anyway, that's how it works for them. So they would say that like literally that the Earth is rotating from underneath the light, and that's causing the fringe displacement. Although that would require a north-south variance, and there's none of that. So that's super unfortunate for the Earth rotating lads. And
your question would be, can you explain the Sagnac effect then?
Me or Toon?
You.
So the Sagnac effect is when you take a light beam, you split it coherently, you split it such that it recombines in a circuit going opposite directions to one another. When it recombines, a fringe shift pattern will be produced if proportional to the velocity of the apparatus.
Okay. Sounds good. All right, guys.
So on the a interferometer that's precise enough, sitting fixed to the surface of the Earth, gets a fringe shift. Why is that happening?
Ether wind.
Now, is ether wind possible inside of a metal container?
Well, that's a good question. So there is a slight measurement in there, but the periodicity that you can measure through the fluctuations is reduced greatly through it. And what was found through experimentation in the 1900s, not 1900s, 1920s to 1930 from Miller, was that when you hermetically seal the device or you use Fermi surfaces to shield it, that actually blocks the readings. So that shouldn't happen because that's showing that light has a hydrodynamic response, right?
But Allan, you know that the most precise interferometers that are measuring the Earth's rotation are in sealed metal containers underground. How are they measuring rotation?
There's still a fringe pattern displacement, and those also use they use a medium in the tubes as well. So, like, are you familiar with the Ginger project and all that?
Yeah.
Yeah.
It's inside the thing. It's inside the thing that you said blocks the ether wind.
Well, it doesn't block it. It doesn't block it entirely. There's still measurements. You can still get periodicity out of the measurements too. It greatly reduces.
But you said it.
No.
Does it block it or not block it? It seems inconsistent there, Alan.
It greatly reduces it. You can look at Miller's work and Yuri Galev's work, where they show that light responds hydrodynamically according to the shielding that's used, right? So, and also the medium that it's propagating through. So when they do it in a vacuum, hermetically sealed in a basement, they get almost no fringe displacement and no periodicity within the measurement, right?
But they do.
It's very, very
but
reduced.
They do. They get 15 degrees per hour times sine or cosine of the latitude, right?
I feel like you're not understanding what I'm saying. I'm agreeing. I'm saying that there's a periodicity that they also measure. That's daily fluctuations.
But you're saying that the ether wind can't get in there.
Who said that?
Miller. You.
Miller said it greatly reduces it. It doesn't say it doesn't get in there, dog.
All right.
That's a good time
Miller enough times to know what he said about it. I've read Galev's papers enough time to know what he said about it. Never said it doesn't get in there. I said it greatly reduces the effects. When you go to altitude and use things that aren't Fermi surfaces for the shielding, you get increased velocity, right? Yuri Galev showed that too, right? So we have corroborative evidence that there's a vertical velocity gradient, right? So if the Earth is rotating, when you take interferometry readings at altitude, it should still be 15 degrees per hour because you're invoking the measurement with respect to absolute space of a hypothetically rotating center point, right? Not an actual mechanism that affects the speed of light.
Okay, final super chat says, interesting to see how people can justify their BS. Don't have to read. Allan for the win, other than the dog responses. So they gave you a loss for that. All right, let's head out of here. We got a debate tomorrow, 3 p.m., I believe. I should probably check that, but I believe it's at 3 Pacific, and that will be Ozian against Shane St. Pierre. I'm just going to make sure the time that I have correct. And it is at 3 p.m. Pacific. All right. So that is St. Pierre tomorrow and Ozian. I forgot the topic, but I'm thinking it's...
Tides.
Thank you. Tides. That is it. Should be fun. All right, guys. We will see you tomorrow. Do your own research. When you do, you'll never again believe all the bullshit you've been taught. Thank you, Toon. Thank you, Allan. We'll see you guys next time. This has been Jeranism.
Thank you, guys.
And DEBATISM.
All right, we'll see you.
Peace.
Yeah.
Thanks.
Yeah. It was nice just hanging out. Now go and hit the bell. Share it with the homies so that they could grow as well. They missing out. Jaren leaves no doubt. If you know what we bout, it's never for the clout. Don't fuck around. Hey, not for the clout. That's too cap. We calling them out. Balls get flat when you cover her out. Jeranism all in your mouth. Truth gets lost like all on the couch, but it's time to get up and make them get out. Uncover her out. Jeranism. We are the crown. Telecasting worldwide. Check the globe is falsified. Space is spinning DFI. All just scientism lies. Telecasting worldwide. Check the globe is falsified. Space is spinning DFI. All just scientism lies.
Who this be? What he about? You say spinning, he said out. About flat earth, it's flat out. He's still standing when you passed out. Globers pound, scream and shout. He can turn you inside out. Yeah, surface deep, he's fell throughout. And he stay grounded, you spaced out.
We gotta run nowhere when we come fact check your facts and match your data. Concept is too abstract, what matters? Try to tune in, but the note get flatter. Tell me I'm flattered. Flatter than pancake batter, now we landed. Jeranism, I'm your captain. Speaking, telecasting worldwide. Check the globe is falsified. Space is spinning DFI. All just scientism lies. Telecasting worldwide. Check the globe is falsified. Space is spinning DFI. All just scientism lies. You know equations to the things you make the symbols for, but ain't really explaining what the symbols for. They try to teach you things against the things we taught before. No point in arguing now, they don't wanna talk no more. Okay, got a bite of the truth and now it's certain. That's what life look like when your mind is certain. Okay, got a bite had a truth and now it's hurting. This what life look like and your mind is certain. Thanks to the east side, thanks to the west side, thanks to the north side, way down to the south side. Thanks to the east side, thanks to the west side, big ups to the north side, way down to the south side. Telecasting worldwide, check the globe is falsified, space is spinning, DFI, all just scientism lies. Telecasting worldwide, check the globe is falsified, space is spinning, DFI, all just scientism lies. Telecasting worldwide, check the globe is falsified, space is spinning, DFI, all just scientism lies. Telecasting worldwide, check the globe is falsified, space is spinning, DFI, all just scientism lies.
That they would discover, but our decision is that it's more profitable for us to go to the South Pole of the moon because we think that's where the water is.
And we're trying to get at what's the Chinese are doing, you think, on the backside of the moon. Do you have any insights in that?
They are going to have a lander on the far side of the moon, which is the side that's always in dark. We're not planning to go there.
And why not? And what's the benefit of doing so?
We don't know what's on the backside of the moon, so that would be something that they would discover. But our decision is that it's more profitable for us to go to the South Pole of the moon because we think that's where the water is.
So why do you think they made that decision? I'm curious.
I have no idea.